presentation. My name is Kumo, and I am a course advisor for ECT. And I would just like to turn your attention to the notifications and the sound. And could you kindly just switch it off for now while the presentation is going on? This is just to minimize any sort of interruptions that may occur during the presentation. And secondly, I would like to just inform you about our Q&A function. So it's right next to the chat box. That's where you can put in your questions, and then we will address the questions closer to the end of the webinar. And for this webinar, there is a certificate of attendance, which will be sent to you within 4 business days from today. And there will also be a copy of the slides and the recording for this webinar that will be sent to your email within 2 business days. So one thing I would like to stress about the certificate of attendance is that you have 2 days in order for you to fill out the questionnaire on the link that will be provided, or the QR code. Both will lead you to the survey, and you need to put in your information so you are able to receive the video recording, the slides, as well as the certificate of attendance. So for this event, I'd just like you to follow my instructions so there are no sort of interruptions or anything like that. So we have a smooth sailing presentation. And just a little bit about ECT. ECT is an engineering specialist, which is affiliated to the recognized EIT, and we deliver industry-driven programs with UK recognized education. So this is made possible by our lecturers who are specialists within the industry, and also by our unique delivery model. And today's topic will be presented by Dr. Abate, which is our lecturer. And the topic for today is performance-based design for beginners, basic concepts and applications. So, Dr. Abate, if you don't mind, you can take control and take it away with the presentation. Thank you.
Thank you, Kumo. Let me share my screen. See my screen?
I can see you, however, I cannot yet see the screen. Or maybe, do you want to take control from my presentation?
Because I have to share the software also. Let me stop it.
Okay, no problem.
Entire screen. Still?
Let me just check.
I scan, yeah?
I see multiple screens. Okay, there we go.
Now you see, yeah?
Yes, sir. So you could just go ahead and start
Great.
the, yeah, you can present. You can click on present, and then
Okay.
it will do the full view for you.
Okay. Thank you, Kumo. I really appreciate. And
No
thank you for attending this webinar. My name is Dr. Mistra, and today we are going to present a performance-based design for beginners, basic concept and application. And in this presentation, we are going to show you not only theoretical part, but we are going to show you also this is a sample ETABS model. So this is a linear model. So we have linear, and we have also another nonlinear model. So this software, we will discuss about it. And if we have time also, I'm going to show you the real life building, what we are doing. So it's going to be interesting. Okay. So if you want to know more about me, you can scan this barcode and you will get to know me. And today we are going to discuss about structural modeling for PVD, performance-based design, including material properties, section definitions, and load patterns and performance objectives based on FEMA 356 and ASCE 4117. And pushover analysis is also another type of analysis. Its implementation and interpretation, we will see it, and evaluating structural performance in the retrofitting and overview of performance-based principles, and focusing on structural behavior, especially nonlinear analysis techniques and performance objectives. And PVD is different from traditional core-based design and why it is essential. These are some of the agendas we are going to discuss today. And at EIT and ACT also, we publish papers which are very critical papers. You can find it here, and you can read these papers. It will give you tremendous amount of knowledge about performance-based and about the modeling part, linear modeling part. You can go ahead and check part 1 webinar we did previously, and you can get information. So today we are going to discuss about why performance-based design is matter. And to know that, at EIT, we did this bibliometric, this paper, okay? This paper, Global Research Trend. And what we did was we tried to see 3,469 PBT related papers. This was from 1983 up to 2024. And we use voice viewer, okay? And we try to see the knowledge, how it's going. So as per our research, what we see is starting from 1981 until 2023, as you can see, PVD was increasing. The awareness is increasing, okay, throughout the world. So what we did in this research was we tried to see preferred journals and leading countries, leading organizations, international institutions, and identified utilizing the Scoopers database. This is what we did. And you can read also the full research paper as we have seen. So in the cost now, the most important part is in the context of seismic hazard assessment, engineering design and comprehensive understanding of this local geological and geophysical factor is very essential. But however, in most countries, in the previous studies, they lacked critical components such as local soil condition, this ground response analysis, topographic influences, active fault characteristics, slip rates, groundwater behavior, and the slope consideration. These kind of things were not included in the probabilistic seismic hazard assessment of the country. So without these points, it will be very difficult to use the current seismic hazard map of a country. So to ensure that this seismic hazard map, it should include this one. And as per our bibliometric analysis, we see that engineering structures journal, they publish a lot. And United States is the country which, do better in performance-based. Again, United States is doing good, and performance-based was the keyword. You see, all these are research, and we were, checking the co-occurrence of the keyword, and the performance-based was the, came out. So in general, from our research, what basically the hypothesis is this one. We already proved it, but the challenge of adopting seismic design code without necessary adjustment, accompanied by the absence of reliable seismic marking in the country, without earthquake recording station may lead to structural failure. In such context, performance-based design emerges as a viable and critical solution for ensuring structural integrity and safety of both existing and new constructed buildings. This is a very important point. So in our research, in our study, in extensive literature review, what we found was code-based design cannot address earthquake design issues. This was the first. And PBD is cutting-edge seismic design technique. And the effect of using prescribed adopted code without amendment is very dangerous. And design approach focusing on force are not adequate. And the shortcoming of seismic hazard maps and PBD was introduced in the United States, and how the earthquake in the Eastern Japan alert Koreans to assess their building code. And all these things were found. Overall, this study provides a comprehensive overview of the research on the performance-based design and identified the key research topics and the future directions in the PBD area. Now, important point which leads to PBD. So as a structural engineer and who is interested in the performance-based design, you can ask this question. For example, does the absence of earthquake recording station and reliable seismic data pose significant challenge for a country without the mean to generate accurate seismic hazard map? This point is very critical because most of, especially in the developing countries, even they didn't have a station, you know, so they lost a lot of earthquake data in the past earthquake data. So now in the generating of seismic hazard map, they don't have reliable data. So if they don't have reliable seismic hazard map, it will be very difficult to rely on it. This is the first question. Now, if we cannot trust now, number one, okay? Now, if we cannot trust our current seismic hazard map, can we rely on a structural design? Now, if you don't trust this one, how can you design with this unreliable seismic hazard map? The answer is evidently no. This raises the question, how can we design structure that perform well in the future, unexpected earthquake? Because this seismic hazard map will give you the level of earthquake, maybe 4, 5, 6, but it is not reliable. That is a problem. So considering the absence of reliable seismic map in the current countries, could performance-based be a viable solution? This is the most important part. So the seismic performance of reinforcement concrete structure designed according to European code and the recommendation is effective or not. This was also something you should consider. And the other one is the consistency between nonlinear time history analysis, this classical model analysis, pushover, this response spectrum analysis, and pushover analysis. We will compare. So these were the most important point. And in general, as you know, we have linear and nonlinear analysis, and we have equivalent lateral force procedure, response spectrum, and modal response history analysis and linear response history analysis. This is for linear analysis, but this is linear static and linear dynamic. And for the nonlinear part, we have pushover analysis and nonlinear modal response history analysis and nonlinear response history analysis. So we have this and this one. So these parts, we will use all this kind of analysis, okay? So at the EIT, this was the research we did, okay? Where we did 44 story and 100 story. The problem was, you know, if the specification of your laptop, you know, if to analyze this as a performance-based, it will take a lot of energy, and that was the problem we faced. But this was the performance-based design we did at the AIT, and we incorporate our linear, nonlinear, linear, and nonlinear, all the, especially linear dynamic response spectrum, linear time history analysis, and everything. All the analysis types were included, and the result was compared. So this was for 44 story and for this 100 story, and this was the property of the building we did. So the organization of the dissertation, what you will do is you have the classical model analysis, equivalent lateral force procedure, and response spectrum. This will be in the linear analysis, and nonlinear time history analysis and pushover analysis will be done on nonlinear. This will be the organization. If you want to do the performance-based analysis, this is what you do. And cycle one, what you are going to do in the linear model, you perform classical model analysis, ALF, response spectrum, and linear time analysis. And the global responses like displacement, shear, drift, stiffness, moment, you have to find it. And classical model analysis, you have to check first and second mode should be translational and third mode should be rotational. So this should be checked. This is in the cycle one. So once you do that, you go to cycle two. Now in the cycle two, you have to change it into nonlinear model, the linear model into nonlinear model, and you have to perform pushover analysis and nonlinear time history analysis. So again, you will find global responses like displacement, story shear, story drift, stiffness, and moment. And the pushover analysis result will be verified by the nonlinear time history analysis. This is what we do. And here, as you can see, we will use target response spectrum. This is linear and this is nonlinear because we add here behavioral factor. So this is the two type of target. This is inelastic and this is elastic. So for your nonlinear, what you do is because you change your building into nonlinear, you will use elastic. That's what you do. Then in the third step, you will compare. So cycle one, cycle two, and you compare the result. Okay. If it is yes, okay. If it is no, then we will take the nonlinear result for verification. In the comparison of cross section again, in the linear analysis, you will get the cross section for beam and reinforcement bar and ties. And for nonlinear also, you will get the same. So you have to check this. And again, optimization will be done. So in the final will be optimization, from the nonlinear result, what we get, we will optimize the linear analysis. And for the nonlinear analysis, you need earthquakes. So to download this earthquake, what we do, you will go to peer website. Let me show you. This is the website. So in the peer website, you will go and you will sign up here, but you have to use your educational institutional email. And once you do that, you go here, MJ Waste 2. This is the database. So once you click this database, the peer ground motion database system will come, okay? And in the peer, you will submit. And what we are going to do, everywhere in the world, whatever earthquake comes, it will be recorded here. So you give the magnitude, for example, you give RGB and all these things you should know. And as per your need, you fill this. For example, fault type, strike slips, normal, reverse SS, normal or reverse, all these things, and the spectra ordinate. And once you fill the type of earthquake you need, if you know the recording station, automatically you can put in the event name and the station name, automatically it will give you. Otherwise, only you give the range of the magnitude, blah, blah, whatever you need, then search record. Then once you say search record, it will automatically, you see, in the standard deviation, it will give you like that. So 1 in suit mean plus standard deviation, it will give you the value. Then as you can see, it will generate around 18 earthquakes. Okay, for example, this is in Taiwan. Most of the earthquake happened in Taiwan as per our research, and it will give you all the information, the magnitude, everything. So once you get this, what you do, we have seismomatch. You bring this earthquake in the seismomatch, and as you can see, for example, this is Imperial Valley, Lenders, Imperial Valley. These are past earthquakes. So we will import it here, okay? We will import it here, and you can see here. Once you have the acceleration, and then this acceleration will be integrated to velocity and integrated into displacement. So what you are going to do, you have to match this one. So for example, you can define As per Eurocode, for example, 0.01 damping ratio is 5 and ground type importance factor like 1, for example. And let's say this is our target response spectrum, okay? Let's say this is our target response spectrum. So as per this target response spectrum, we are going to match it, okay? So when you say do matching, the software will match the ground acceleration we downloaded, and in a minute, it will give us the result. You see, it's okay. Now matching is done, okay? Now this is matched. Ground motion, this is, you see? Now, this was the original earthquake. This is the downloaded earthquake data, and this is target response spectrum. As you can see, target. Now, wait, after matching, you see, this is the almost the curve is okay. Yeah? So from 0.5T until 1.5T, the earthquake data, it should be up from your target response. This is how we do in the matching and scaling. So we will come it in the later. We will come later. So this is the earthquake we use. Okay, lenders, most of this North Ridge, all this the year it happens, recording station magnitude V30 PG values, and this is the mechanism strikes and normal obliques, and this one is SRSS. For the combination, because we are going to use 11 earthquakes and we have to add it up. Okay, so ETABS also has the capability of, matching. You see, this is matching. You can match it in frequency domain or time domain. Both domain you have the option, okay? You bring the earthquake data and you have target response spectrum, and we match it. So ETABS also match it, okay? Instead of seismo match, you can use this as well. This is how we did the matching, okay? Because this is the earthquake data directly we downloaded from peer website, and this is the target response spectrum, and this is the matched one. So this is how we do. So classical model analysis, as I told you, the first mode and second mode should be translational, and the third mode should be rotational. So is my structure safe? Now, the most important question is my structure safe? So as you can see, there are hazards from earth, water, air, fire. We will get a lot of danger. And as you can see, disaster is other times vulnerability and exposure. And as you can see, we have risk. So how modern code intend to ensure safety? The first one, they define appropriate estimated hazard or load level. They give us this one, it's okay. Again, define procedure for analysis and design. This is the other thing. And provide specification for construction and monitoring, and prescribe limits on structural system, members and structures, and provide rules for detailing. And all these things, hoping that they will reduce vulnerability. So safety requirement gives acceptable solution and prescribe procedure, rule limits, and mostly based on experience, and it's always rational, all these things. So it is okay working with the code, but we will see why performance-based is important. So in the prescribed code-based, the public always, they will ask, will the building will be safe? That is their question. So the owner will ask you, will the building collapse? Will it be damaged? Can I use the building after given earthquake? How much will be the repair cost, and how long it will take repair? And can I make building that will not be damaged and will not collapse? This is a question from the public side. But the structural engineer, what at the code-based level, the structural engineer will say what? I'm not sure, but I do follow the code. That is what he said. Because if you follow the code, always the safest side is DC ratio. If it is less than 1, you are safe. If it is greater than 1, it is unsafe. That is what the code-based we are following. Even we have the safety factors, okay? Even this DC ratio, now the problem of DC ratio is in the demand side, again in the capacity side, we have a lot of assumptions. For example, load and pattern. You see category of load, approximation, statistical averaging. Again, in the load case, We have directional and vibrational load pattern analysis, often linear, elastic, and actions computed each load cases. Okay, P, V, M, shear force, moment, value, interest from analysis, and factor. We have load combination, and we will factor it. Again, action envelopes. Maybe we will take maximum or minimum or something like that. So design action sets. All these things are not, these are approximations, okay? Again, in the capacity side, in the material, we will assume the property based on test and statistical averaging, again, section, assume size, all these things, as you can see. So we are assuming even the DC ratio, which the engineer saying is safe, it has its own assumption. That's why in the code, it's a little bit difficult. So as we have seen, we have linear in linear analysis, and we have linear static and linear dynamic analysis, and we have linear static and linear dynamic analysis. So this all equivalent response spectrum, modal response spectrum. This is the use of mode shape. All this one and this one use the use of mode shape. This one we use a step direct integration, step by step direct integration. We use this Rangi-Kutta and other step-by-step integration method to solve the general equation of motion. So this is why performance-based is required. Now, as you can see, we have MC level of earthquake. And from MC, 2/3 will be dB level, yeah? Again, we don't design on dB because we need design level, yeah? The design level will be, we have R factor, okay? We have over strength factor, okay? So over strength factor we use for coupling beams, and you want to some ductile over the period of the building, yeah? So this gray area is ranging from this 1.5 to 8 or 1.53. So this is a guess. But in the PBD, what we say, why we guess like this, okay? What PBD is saying, get the real stress strain curve or moment rotation and the capacity of your structure, and apply the load, check service level and get the serviceability, and check MC level and check the ultimate limit state requirement. So in this way, no need to guess. That's what the performance-based is saying. So as you can see here, we have R factor, omega factor, and the large range and design level. The design curve could fall anywhere between design level and this dB level and the design level, and code value from here to here, and even tables are provided. But performance-based, the key point is check collapse prevention, ensure structure will not collapse under extreme earthquake, and this one service level will give us the check serviceability and ensure structure will remain functional undamaged under frequent earthquake. So we have two, as I said, MC level and this one, MC level and service level. So conclusion, why performance-based design, explicit check for ultimate limit state and service limit state leads to realistic and capacity-based and risk-informed design. That is how performance-based is done. So we have intuitive design. We start from the intuition, then code-based, then performance-based, then consequence and risk-based design, then resilience-based design. This is how it's going. So as I told you earlier, just you have the section and know your stress strain curve, and you apply this moment rotation and stress strain curve into your building and change your building from linear to nonlinear. Okay, then use pushover analysis and nonlinear time history analysis, and you will get the result. This all what is performance based. This is what it's talking. Okay, how we get the real strengths. For example, we use in the performance based expected strengths typically 30% and 1.17% for steel. So for rebar and for concrete strengths, you will get the expected strengths, and reinforcement detailing also required initial. That's why we need required initial code based. Okay, this is I will come in a minute. So, once we get the cross section from the initial linear code based, we use that one to the translating to nonlinear model. Okay, once you get linear analysis, then you will change it to nonlinear model as we have seen in the beginning. So convert the model to nonlinear from, for example, plastic hinge modeling or fiber hinge modeling. Assign appropriate hinges for beam column. For us, we use plastic hinge modeling for beam and column, and for shear wall we use fiber hinge modeling. Then define moment curvature, moment rotation. So we use moment rotation, and after we do that, nonlinear. Why? So we use nonlinear modeling, capture both local and global responses, because once you give the moment rotation curve, once you apply the force, you have different labels. IO, okay, immediate occupancy, collapse prevention. We have a lot of labels. So once the force comes, it will give you the capacity. Okay, it will give you the capacity. That's why we use. Okay, so performance-based design, the process will start from architectural design, okay? You start from architecture and you model linear modeling, then code-based design. And for alpha and the response spectrum will do the job for you. And because at this point, alpha or response spectrum, then determine the true capacity of the building as per linear analysis. Now change the model to nonlinear, then apply service level and MC level, section and modification of ground motion as we have seen now. We download the earthquake, modify, scale it, apply. And once you do service level and MC level, for the service level, no problem. You can use the response spectrum. For MC level, you can use nonlinear times tree analysis. Okay. Now check the performance assessment based on SLE and MC level. So if the check acceptance is okay, then finish. Otherwise, change the design. What you are going to do, you go the linear analysis again, and you have to come all the process. This is how the performance based is designed. So main consideration, which item checked for the performance, modal analysis, base shear, base moment, all these global responses and DC ratios, everything will be checked. So we have, as we have seen, operational level, immediate level, life safety level, collapse prevention level. As you can see here, as we have seen, once you give moment rotation curve, and we have these levels, okay? So depending on the force, you see from 0% until 99%, because you have the capacity, yeah? So when the earthquake comes, depending on different level, you see, until it's collapse, but until it's extremely damaged, but not collapse, okay? Collapse prevention means you have extreme damage, but not collapse. Life safety level and some. So you will agree with the board, okay? The PVD board, which is the key performance. For example, stiffness, stability, strength, deformation, drift, ductility, damage, damping, energy dissipation, and acceleration. So these key performance indicators will be agreed with the PVD board. Even you need a board to accept the performance levels, okay? Then as per that performance level, the PVD will be done. So PVD in a linear dimension model. Okay, so now let's see the performance-based seismic design. We have seen it, but in the code-based, prescribe the specific criteria and procedure that design and construction must confirm. Okay, this is the code-based approach. Engineers do not actually evaluate the ability of the structure to perform as intended by the building code. This is the limitation. Again, limitation to in use of structural systems. Some structural systems you cannot. Rather, the engineers is able to perform that because the building complies with the prescriptive requirement. This performance will be obtained. This is in the code base. But in the PVD, we have flexibility and innovation. For example, overcomes the shortcomings of building codes for the seismic design, in which the performance objectives are considered implicit, and guarantees the safety of the building with better reliability by explicit evaluation of structural performance under different level of earthquake, and to substantiate expectations to specific prescribed calls. So you can go ahead, and this is the flexibility and innovation of performance-based. So let's see now what is operational level, immediate life safety, and collapse prevention. Look, in the operational level, negligible structural and non-structural damage, okay? And occupants are safe during the event, and utilities are available also, like water, light, electricity, and all these things. Facilities are available for immediate once the earthquake come and stopped, and people can start their regular work, okay? The loss is less than 5%. What about immediate occupancy? In the immediate occupancy, negligible structural damage, occupant safe during events, minor non-structural elements like HTV and something, and building is safe to occupy, but may not functional, okay? Maybe they can occupy, but it's not functional. And limited interruption of operations might happen, and the loss will be less than 15%. And life safety, we have significant structural damage. Some injuries may occur, as you can see, extensive non-structural damage, and building not safe for reoccupant. This is the loss is less than 30%. What about collapse prevention? This is extensive. This is near collapse, structural and non-structural damage, as you can see here, significant potential for injury, but not wide-scale loss of life. This is extended loss of use. This is repair may not be practical, and the loss is greater than, but not collapse. That's why we see collapse prevention. So you can check in FEMA 451B all this explanation. And as you can see, we have 3 levels of earthquakes. We have the service level, we have DB level, and the MC level. 50% probability of accidents is 30%, and this is 10% in 50 years. This is 2% in 50 years. So all these are what we have discussed, and this is now you have the idea what is IO, life safety, and collapse prevention. So this is the, as we have seen, we have MC level, and the 2/3 of MC level is DB level, and service level, we have 43 years of return period. And the damping ratio, we use 5% and 1.6% for service level. This is also very important, and this is the how to calculate. The other important is level of earthquake. We have seen it now, 50% 30 years, and period the generally 1.5 to 0.5 damping, and serviceability, a structure to remain essentially elastic with minor yielding of structural element, minor cracking of concrete, and minor damage to structure. This is service level check. What about MC level? This is 2% of probability of accidents in 50 years. And this one is collapse prevention. Structure has a low probability of collapse, which will demonstrate implicitly through analysis that indicate the structure has a stable, predictable response to this level, shaking at response level, which do not result in loss of gravity load carrying capacity, okay? So this is the 2 levels we check in performance-based analysis. So we have seen it, all this MC level, DB level, and service level, you can go ahead and see. The other thing, let's go deep now in the technical part. For example, service level evaluation, use linear model, and as I told you, response spectrum analysis you can use, and accidental acceleration are not considered in service evaluation, and critical damping from 1.5 to 0.5, and load combination from dead load, live load, and 100% of earthquake in the X and 30% earthquake in the Y. Okay, this is what we do. This one is for this quasi-permanent load cases, what we use. And let me check, sorry. Okay, so MC level, MC evaluation, sorry. So expected service live load with 25%. This is for quasi-permanent load cases. So R factor, omega factor, CD factor are all taken as unity at this point, okay? DC ratio should be less than 1.5. This is deformation control, and if it is force control, it should be 0.5. Strength clarification, use expected material properties, strength reduction 1, and story drift 0.5%. for service level. Okay, this is expected means 1.3 for concrete and 1.17 for reinforcement. And MC level evaluation using a linear model in a linear response history analysis. 11, as we have seen, we have 11, and generally 2.5% of constant modal damping will be used, and average of this 11, because we have 11 earthquake, yeah? Then we have 11 global. For example, shear force 1, shear force 2, shear force 11. So you have to RSS these values. So deformation control means this is deformation control, and this one is force control. This is brittle. This one is ductile. You see, as you can see, this is reliable. And we have also hysteresis loop. Okay, different hysteresis loops. So this will be done in the laboratory by loading and unloading forces, and it will give you the backbone curve, as you can see, because when you load it, it will go up, unload it, it will go down, load it, and it will go like this, okay, rotating. Then this backbone curve will be idealized like this, okay, bilinear or trilinear backbone curve, and it will be used as, we use it for our design. So this is the behavior. Okay, for ductile, what is the force deformation relationship for deformation control and for force control? If it is deformation control, behavior is ductile and reliable, as you all know. And if it is shear control, it will be brittle. This is the most important thing. The other most important thing is nonlinear fiber modeling. As you can see here, this is the stress strain curve. So in the stress strain curve, you see this one, unconfined. If it is unconfined, it is very, the strains, the ductility is almost, you see, vary. But if you make it ductile, your structure, then the capacity will be higher. Okay, this is very important. So ductility, the making ductile is in your reinforcement. If it is, this is your section, then you have to try to make it ductile, okay, as per the detailing requirement of the board. So this is confined concrete, and this one is unconfined. So most of the time, the confined is in the edges, okay? Then the unconfined concrete will be in the middle. This is for the rebar, and this is for concrete fiber. So stress strain for concrete and rebar. This is how in the fiber modeling approach we use. Again, some of the characteristics, for example, when you do performance-based, peak transient, drift transient means in the first the beginning of the minutes, maximum mean value not exceeding 3%. This is for the drift, and maximum drift shall not exceed 4.5. Okay, and maximum of the mean value should not exceed 1%, and maximum drift shall not exceed 1.5%. And coupling beam in elastic rotation, this is as per ASCE 4117 limits. And column, axial pressure interaction and shear. This ASCE, we will see it in the minute. Very important guideline, okay? Shear wall also, as you can see, axial straight 0.05. What is 0.5, 0.2? We will see it in a minute. And unconfined concrete 0.005, and intermediate confined concrete 0.04. This is the formula you would use. And fully confined 0.01. Do you see the difference? This is 0.003. This one is 0.015. So the confinement is very important. Shear wall remain elastic. And again, for girder, so as you can see, this is some of the criteria as per ASCE. After you do the performance-based design, you have to check a lot. So acceptance criteria, as I told you, there will be a performance-based board. They will accept what will be the drift, what will be stress strain, which should be IO or collapse prevention, immediate occupancy. All these things should be agreed in the acceptance criteria in the board. Okay, this is only for sample we give you. Now, this is the most important point. As we have seen, ASCE 4117 model. So as you can see, we have 1, 2, 3, 4 criteria. Okay, they have 4 criteria, and they have A, B, C, and they have modeling parameters, and they have acceptance criteria. Because now in the performance-based design, the most difficult thing is to know the capacity of your section. Okay, you can go to laboratory, but all the engineers you can get from laboratory result, but always you cannot go. So different repetitive experiment, ASCE41, they give us the capacity of your section as per, for example, the first one is condition 1, beam controlled by flexure, then beam controlled by shear, and beam controlled by inadequate development or splice along the span, and beam controlled by inadequate. So all these things, they give you here what they mean. For example, conformity, non-conforming, conforming, all these things, they give you here all the detail, okay? So as you can see here, rho minus rho prime over rho balanced. This is the most important thing. That's why now let's look. Once you do linear analysis, you get the section and reinforcement bar. As per that section and reinforcement bar, you come here and you check, you get this from linear. That's why linear analysis is very important for before you perform performance-based design. Because once you do linear analysis, you know the section, you know reinforcement bar. Then you come here and you use these row ratios, okay? And you check your beam is conforming or non-conforming here, okay? They will give you what is conforming, non-conforming. Once you know that, again, you use the shear force, B, D, and FC prime, and using this, you know which level you are. Then once you know this, then you know A, B, for example, let's say this is the row, okay? Now you know A, B, C, and IO, LS, CP. So A means this is A. You see, this is force deformation curve. So the A value is this one. The B value is this one. And the C value is this one, okay? Then IO, life safety, immediate occupancy, and collapse prevention, you see? So now, from this, you see, for force deformation curve, easily you can know the capacity of your curve. That's why linear analysis should be performed first. If you remember in our workflow, that's what we say. So let me take you back at this point in our model here. So as you can see here, this is our building, okay? So last time, as we discussed, you have to start from linear analysis. So in the linear analysis, in our first webinar, we show you how to design, okay? We show you how to design column, blah, blah. So as you can see here, we have material. For example, we have here, this is the concrete weight, volume, and we have elasticity, Poisson ratio, coefficient of thermal expansion, shear modulus, and everything is given here. And as you can see here, this is for material definition. And still also we have rebar, for example, rebar for or 500, okay? For the rebar also we have weight modulus of elasticity, collapse, this coefficient of thermal expansion, and everything is given here. Minimum yield strength and minimum tensile strength, and everything is given here. So you have to start from the definition, then we have to go to section definition, and you give beam section, for example, 50 by 50. This is the section we give 50 by 50. And last time we discussed also the shear area and the torsion, because in the beam and column, we have to give 0.5 after as per Eurocode. So you have to take care of this part, okay? And the other thing, the column also the same, the modification. Let's see. As you can see here, we give for the column also the same. And for the definition of slab, you have to give, for example, flat slab here. For slab, membrane action and bending action, yeah? We have membrane action and bending action and shear action. The shear action, this is very thin, yeah, L over 10, okay? So if it is lower than 10, so what we don't need, because shear action is very important when it is raft foundation, yeah? In the raft foundation, the shear action also available. So for this part, for slab, for thin, we don't use. But the other one, we give modifiers, okay? Very important. And diaphragm, this is for the center of mass. Last time, let me show you the center of mass. Here, where is diaphragm? Nonlinear hinges and moment. Okay, sorry, here. Diaphragm extent, yeah. Okay, so let's turn it on. This is the center of mass, you see, plan. Okay, second floor. So this is the center of mass, okay? And in the center of rigidity, last time we see, to get the center of rigidity, you see, calculate diaphragm center of rigidity. You have to tick. Otherwise, center of mass and center of rigidity will not be calculated, okay? So what we do, let's go back and let's turn off this part, diaphragm extend. Okay. Sorry. Okay, 3D. The other thing, load pattern, we have dead load, live load, and earthquake. This one also we discussed last time. ELF. This is everything you have to get it from the code, okay? You have to get it from the code. And we have also load combination. We have ultimate limit state and serviceability limit state. For the ultimate, we use only 1.35 and the live load is 1.5. Just the overview I want to show you, because once you design, okay, once you design, the first thing you have to check is mode shape. For example, mode 1, let's check it. Sorry, mode 1. And very quickly, let's check. Because the first mode and the second mode should be, you see, translational. So let's start. The animation, I want to show you the animation. Okay. So this is pure, you see, this is pure translation. Again, the second mode, let's check it. This is also pure translation. The third mode, it should be torsion, okay? So let's check it. Okay, so this is the most important point you have to check. Once you check this and once you run in the analysis, let's go to reinforcement bar and let's see the rebar. Okay, this is the rebar, you see. Let's make it elevation. Now, in the linear, you see, you get now the rebar. So let's check the result. For example, okay, it's a little bit slower. Okay. What I want to show you, once you get the rebar, longitudinal rebar, okay, from your linear analysis, let me, okay, plan. Let's make first floor and like this. Okay. Okay. This is the reinforcement bar the software will give you. Now, where we will go to nonlinear analysis. The same linear analysis, we will change it into nonlinear. How you change nonlinear? You choose the section. We show you this one also. We choose the section and we assign. Okay, we come here. We assign frame. You see hinge. Now it is run already. It's not working, but you make it hinges and you're gonna apply the hinge. Once you apply the hinge, now your building has been changed from linear analysis to nonlinear analysis. Now your building is capable of capturing the capacities. So to see the capacity, for example, let's go here and load cases, for example, pushover. Okay, pushover. Let's start from number 1. Now, when we apply earthquake, you see already the building now capturing which level is your building. For example, let's go to second level. In the second level, already most of the building capture, the capacity is already in this range. Okay, it's okay. Now third, you see some hinges are forming. Let's go to fourth. Let's go to fifth. You see, still, you see now here blue is formed here. 1, 2, 3. Already we are in this range now. Now let's go to 6. You see, in the base also some hinges are formed. And 7. Already here, you see. And let's go to 8. Still in this range, And 9. Still we don't reach this collapse prevention. And 10. Again 11. Okay, 10 is the last. So as you can see, our building is safe. Nothing is past the collapse prevention. So this is how the performance-based is done, okay? This is how the performance-based is done. Okay, you see? Some of now, at the 10 already, these areas, you see? Some of the base, especially in the base area, we have collapse prevention passed already, okay? So let's start it again, because that one is on the colored base. So number 1 is this. Number 2 is this. Already in the push 2, already some hinges are already past collapse prevention. Number 3 already here, but almost in the base, you see? Almost in the base, you see? Something like that. So it will give you, now the engineer has the capacity to see the performance of the building. And what I want to show you here in the frame, let's go to here. Let's hold all the hinges. Okay, these are the hinges which was created. Now, for example, let me take you here. Let's modify. You see, this is the backbone curve of the ETABS. It will use the reinforcement and the cross section, and it will give you the points. Okay, it will give you the point. You see A, B, C, D, E, A, B, C, D, E, and it will draw the capacity, moment curvature curve. Okay, if you moment rotation, this one is moment rotation. And in the moment rotation, you see immediate occupancy, life safety, and collapse prevention. Already the capacities, the criteria are already included. Okay, already included. So ETABS has a capability to capture where is the immediate occupancy, life safety, and collapse prevention. But from where it will get it from the linear analysis, and I will take you back, and it will start from here 0 because the yield no problem, yeah. So the yielding is divided by the moment, and it will come at 1 here. So the ETABS doesn't capture until the yielding point, no problem. So that's why it will give you like that. So these are all, you can go ahead and see, for example, PAIM for the column also, we can see modify. As you can see for the column, you can go ahead and check the angle, okay, the interaction curve, the angle you can change, and you can see the immediate occupancy, life safety, and collapse prevention. And now, the most important thing at this level, what you should know is that now our building from linear analysis, okay, from linear analysis to nonlinear analysis, now we have the capability to check the performance, okay, to check the performance. So before we go that, this is our real project, okay. This is one of our real project. In the real project, for example, in the load combination, let me show you one load combination. We have around more than 127 load combination because we have wind load combination and we have imperfections also. So the imperfections will be joined with the earthquake and it will make it more than 128, 130, 40 load combination. So when I say here the load combination already, for example, for this one, for example, for our linear, we use only 2 load combinations, okay, for just for you because ultimate and serviceability. But we have earthquake and we have wind loads also. Okay, let's go back. And so now you know the beauty of ASCE, yes? Because ASCE now you don't have to always go to laboratory and you don't have to always know what is the capacity of my section or something like that. You don't need to do that. Because once you know the reinforcement bar and everything, the section and the shear force and the B and the D means you have section here, you have the depth of your section, and you have the B, and you have the shear force and FC prime, the concrete quality, and you know the reinforcement bar, rho prime, okay, compressive, and this is for tension, and this is for compression, this is rho balanced, and you will check only conforming or non-conforming, and you know the value of your A, B, and C, okay, and immediate occupancy, life safety, and collapse prevention. Then now, your building is capable of capturing the capacity of your building. This is a performance based, okay? So 1, 2, 3. Now, when I say 0.01, 0.02, 0.05, 0.06, what is it? 0.01, as you can see, the building, your beam is intact, yeah? This was done in the UCLA in America, okay? So when we say 0.02, let me go back here. You see, when we say immediate occupancy, for example, immediate occupancy 001, for example, collapse prevention 005 means. So 005 means already it is collapse. So when your rotation is 0.05, it means your building is already collapsed, but it's not, it's not collapse. It's already extensive damage. Okay, but 0.06 already collapsed. So collapse prevention means extensive damage, but not collapse. So if you want to know more about these things, you can go ahead and check the capacity spectrum method. For pushover, we have capacity spectrum method, displacement coefficient method, and FEMA 440, and improved this NCPs and modal pushover analysis. All this you can use for pushover analysis. So now at least you have the idea what is 0.01, 0.02, 0.05, okay? Because this is the way of doing performance-based analysis. So typical PBD we discuss now. Now it will be clear because we start from linear modeling. We apply alpha and response spectrum, determine the capacity. Then we change the model, nonlinear model, and we check for service level and MC level. And then service level evaluation using linear analysis response spectrum and the MC level with nonlinear time stay analysis. Then check the performance. If the performance is okay, if it doesn't pass collapse prevention, it's okay, finish your building. If it is not okay, then repeat. So you have to go to linear analysis and you change the section, the beam, the column, and everything. Again, you run the linear analysis and follow this step. That is what it means. So this is the PVD is very wide. So it starts from the client, then the architect always start the building. Yeah. Then we have structural engineer. Then the structural engineer, we have PVD specialist. Okay. And we have site specific consultants and PVD peer reviewer. PVD is reviewed also like paper, because it is a very long process. So it should be reviewed. And these are applied ATC guidelines, FEMA, NEHRP, peer ground guideline for tall buildings. And this peer we have seen now, we extract also download earthquake, yeah? TBIs, all this. This ASCE 4117, now you know it, yeah? So very important guideline for performance-based, and all this you can use for as a guideline. So this one hinge assignment we have seen now how to assign for beam, okay, and all these are for ETABS, okay, pushover load, how to apply pushover load scales, all these things. This is load combination, load cases. We have seen it now. This is we have seen it now. Hinge assignment, as I told you, moment rotation, this IO, LS, all this is for the column. Okay, this is for the beam. So now let's compare now. This is the main reason why PVD. So at the code base, the engineer says, I don't know, because I use the code. If the building fails, I am compliant. That's why in the world now, all the buildings we hear every day, collapse, collapse, collapse. That doesn't mean the engineer doesn't comply with the code. Okay. That's why the engineer says, I am not sure, but I follow the code. Okay. That's why when the building collapse, will it damaged, or can I use the building after giving earthquake? All these questions you ask him in the code level, the engineer is not sure. But in the performance-based level, now as we have seen, we know the performance. At what push, what is the IO immediate occupancy, collapse prevention, life safety level, we know it. So at this level, will the building collapse? Will it be damaged? Can I use the building after given earthquake? How much will be the cost? How long it will take repair? Can I make the building that will not damage and will not collapse? Now the structural engineer will say yes. And I can answer all these questions because he knows at what level which column will fail, as we have seen now. When he push at what level, the building will hinge will be formed. So he can change the section and he can change it from life safety to immediate occupancy or something like that. So by shifting our paradigm from prescriptive code-based design to performance-based and explicit performance evaluation, we can now answer all the critical questions. We now have clear detailed knowledge and the necessary tool to address public concern. Questions that could not be fully answered under traditional code-based approach now is answered. So this is the main reason why PVD and similar techniques are so important. So now the problem is how to convince the client. Now we know that PVD is good, but how can we convince the client? So we have to start with the client. If the client asks, what is the benefit of applying PVD? He will ask you, because PVD will cost a lot of resource, yeah? So the client should pay. And the client may ask you, I need the building will be resistance for earthquake 7 or 8. Now the engineers become architects because now the code, if you follow the code, and for example, if you choose one city like Dubai, for example, the maximum capacity as per seismic hazard map may be 4. That is what the code says. Okay. And the seismic hazard map says 4. And the engineer will design by 4. But when the earthquake 5 comes, nothing will resist. You understand me? Now, why we limit the client? If the client has money and if he can pay, we can say we can design the building for capacity 5, 6, 7, 8, like for example in Japan 9. Why we limit the client? That is the most important thing. So he will ask you, even if it costs him money, but safety will be guaranteed. Then our response shall be, your building will be achieve higher and certified performance compared to buildings that do not follow PVD approach. In addition, you will receive a performance guarantee and certificate from the design consultant. So the design consultant should be responsible, okay? Because you are doing performance-based design and you have to assure at what level of earthquake you know how the building, that is the beauty of performance-based. So at this is, you can go and check the performance of the building. For example, as you can see here, this is hinge B2H46. You see, it didn't pass the yield even. It will reach from here to here until yield point, but it didn't go, it didn't pass to the, and it will give you also immediate occupancy, life safety. You see immediate occupancy, life safety, and collapse prevention in the moment rotation curve. And you can get a lot as the whole the building. This was what we see: immediate occupancy, life safety, and collapse prevention. It gives us the whole, the overall of that performance of the building, and the stress strain curve for concrete, and it will give you also, you see, and for steel also, immediate occupancy, life safety, collapse prevention. So it will give you where, if it is passed, you see here, immediate occupancy, life safety, collapse prevention. So whenever the earthquake comes, if it is past collapse prevention, that means it fails, yeah? So you have to change the concrete quality. For example, C45, then you have to change it C60, this C35, then make it 40, 45, something like that, until it complies with the level of earthquake you want to design. So this is all global responses, shear force, moment, displacement, all these things. You can, this one, you can go here. Let me take you here, 3D. And what you can do, just the display, and what you do, cumulative response, this one, story response plot. And industry, for example, let's choose case, let's see alpha, for example. So as you can see, we have displacement, we have drift, we have displacement again, story drift, and we have shear force. These all are global responses. And we have moment, and we have stiffness, everything you will get. And if you want also display combined response, and it will give you all the combined, okay, at once. So this is the earthquake, and I will show you in a moment once it's downloading. So once the displacement, the drift, overturning moment, and for the shear, everything we will get, and the software will give you. Okay, just 1 minute. It's okay. It's downloading. Okay. Okay. So it's download. It's taking time, and once it's finished, it will give you, and you can select. Okay, it comes here. So you can select the, even if the earthquake, the lowercase here, and you can the steps and other things. Okay, this one is downloading the displacement part. This, if you choose the earthquake, you know, once it is the earthquake going, it will give you the responses all together, the shear force, overturning moment, displacement, and everything. And you can choose, you can animate and everything. Okay, so it's taking time. Let's go back to our presentation. So what we are going to do, this is a global responses. Now you know from where it comes. This is shear force and everything. And this one also, the DC ratio, you can see it from this one is, for example, for DC ratio result for immediate occupancy, only for immediate occupancy. This is for life safety. This is for collapse prevention. Okay. And you can go ahead and see, for example, for stress level from 0 to 0.5, for example, 50% of cracking strain. Again, from 50% to 70, this is cracking strain. And from 70 to 90, this is cracking strain. Because you have immediate occupancy, and from the immediate occupancy level, you have your own. You give the stress level 50%, 70%, 90%. This is how the immediate occupancy level gives you. This is life safety gives you, and this is for collapse prevention. This is all the same. Okay, the same thing we did. So overall discussion on the two in our research, we try to see all, as you can see here, dynamic linear time strain analysis, response spectrum, and pushover analysis, nonlinear time strain analysis. And in the X and in the Y, we try to see which response gives more. And as per the code requirement, always static like equivalent lateral force procedure will give higher result. That's why when we make dynamic analysis like response spectrum analysis, we have to scale it up until 80% of the dynamic, the static analysis result. So that's what we observe in our here also. Most of the result for response spectrum was higher because response spectrum times also omega factor, because when you multiply it, it will give you higher result. As you can see here, higher result. Okay. Here also higher. Here also we have higher result for response spectrum. So key steps for performance-based design. So choose the performance label and the design loads, define demand capacity measurement, drift plastic inches, shear etc. Get the deformation and force capacity as we have seen here. We know from ASCE 41, then strength from ASCE, we took that deformation and calculate from experiment. No need experiment now because from ASCE we can find, use structural analysis, then calculate DC ratios and change the design. So most of the papers are published. You can go ahead. It is very helpful for you in the MDPI we publish. And so this was the presentation. I think from my side, we have seen what I want to show you, everything we have seen now, and especially in the load combinations. In the load combinations, especially because most people ask load combinations. So in the load combination part, not only two loads are there. As you know, we have arithmetic loads and quasi-permanent loads like dead load, okay, like 1.35 plus live load. Then this will be reduced by psi2 factor, then plus arithmetic in the X and plus arithmetic in the Y. So if you take 100% arithmetic, and this will be 30%. That is how we do it, yeah? So in the Euro code, this is equation 610, okay? That's what it gives. And when the load is, for example, leading and accompanying, okay? And favorable and unfavorable. So in this case, the psi2 factor will be given for the leading one, then the accompanying one. Then for when it is favorable and when it is unfavorable. This is the rule which is found in the Euro code. That's why here, using this combination, the load here, what we have seen here in the load combination, if, for example, here, this one is for imperfection load because we add imperfection load here. One thing you have to take care is in the imperfection load, if you go to preference, and if you come here, theta, this theta value 0.05. If you give 0.05 here, and if you add imperfection there, it will double it, okay? You have to take care. So if you add the load combination imperfection loads here, for example, if you add here, you have to make 0 that one. That's why. For example, what I want to show you in the wind load, for example, all this imperfection, this is gravity, seismic, okay? For example, Let's check this one. This is also imperfection. Okay. So the imperfection load makes it almost huge because all the imperfection load should be with seismic gravity, and the earthquake and the imperfection will be attached. So most of the time when we say earthquake, this load combination, you have to take care. So what other things? That is the most important thing about performance-based design. So this is the procedure, and from my side, I think I am done. Thank you so much. I really appreciate. I hope you get something from this webinar. Thank you, Kumo.
Thank you so much, Dr. Bate. That was very insightful. Me, myself, as an engineer, I did find it quite interesting. And the fact that there's formulas and softwares for this. So that's pretty cool. I guess one day I could be an engineer. And thank you to Abdullah for attending the presentation. So I see that there are no questions. And with that being said, we can call it a day and wrap it up. Thank you so much and have a good
Thank you
day.
so much. I really appreciate. Thank you, Kumo.
Thank you.
Thank you.
Bye.
Oh.